Good evening, everybody. A very warm welcome to the Second World Congress on Nanotechnology. My name is Associate Professor IRTS Dr. Sachin Sharma, and I'll be representing Taylor's University School of Engineering from Malaysia and Lincoln University College School of Engineering, Malaysia. And today I will be presenting on the study on the corrosive performance of acrylic epoxy based coatings, the significance of its electrochemical impedance evaluations. So in my presentation, I will cover on the literature review, problem statement, novelty, research objectives, experimental methods and materials, results and discussions, and finally, conclusion. So, as we all know, corrosion has been a serious threat to both society and economy in the past years and even today. Therefore, a significant amount of efforts have been devoted globally by the researchers to come up with prevention strategies to prolong the corrosion attack on steel structures. In other words, corrosion losses have resulted in affecting 3% of the world's gross domestic product. And therefore, over the years, various modes of corrosion inhibitions were developed and enhanced, such as the barrier protection, cathodic protection, self-healing, anodic passivation, active corrosion inhibition, and etc. And figure one actually illustrates the concept of the corrosion protection, and figure two explains the significance of graphene-based materials. Okay, the inclusion of graphene into the graphene nanoparticles into the polymer matrix, which actually enhance the barrier properties of the corrosion coatings. Okay, so why the inclusion of nanoparticles, not only graphene, but also graphene oxide and its nanomaterials, other additives like tin oxide, titanium dioxide, silicon dioxide, zinc oxide, and etc. have actually enhanced the corrosion protection performance. So why nanomaterials are very good, such as graphene-based materials? Because they have high energy barrier, high surface area, high electrical conductivity, good electron acceptor, okay, and they also have high Young's modulus and also other properties, which not only is suitable for the corrosion coatings, but also for other applications such as toxicants, biofouling applications, pathogenic microbes, and etc. So our main concern of today's topic is about the study of the acrylic-epoxy polymer matrix coatings, right? So as I mentioned earlier, that corrosion has been a serious threat. So the annual immense cost of 2.2 trillion US dollars was resulted, therefore affecting the GDP, world's annual GDP, around approximately 3%. So this figure actually explains how the corrosion process occurs on the steel structures or metal structures in the presence of water, oxygen, and electrolytes. So due to the ease and scalability, so this is about the novelty. So how the latest classifications of corrosion protective coatings became popular. So the reason is behind that is because in the past, decades ago, traditional or conventional coatings were used, whereby only single resin was fabricated. Okay, however, to enhance the stability and the lifetime of the metal substrates, we also use other types of coatings, okay, incorporated with multi-functional, or we can call it as smart coatings. So why are we actually using multiple coatings, okay, or we can say smart multifunctional coatings, whereby it consists of the combination of two resins. So in this case, we are using acrylic and epoxy. Okay, we are combining and therefore it is known as multiple coatings. Why it can reduce the rate of the corrosion process is it's mainly because it prohibits the formation of fast channel for corrosive ions, and because of its enhanced compactness, it is able to obstruct the flow of the current. So the formulations of organic paints, whether it's containing two resins or with the addition of fillers and additives, they have demonstrated the most effective approach. So one important thing that we need to know over here is that corrosion cannot be prevented. However, it can only be prolonged. So the research objectives over here is, as I mentioned earlier, we are actually fabricating multifunctional, or we can call it as smart coatings. So the combination of acrylic epoxy based coating systems, composite coating systems, and we want to investigate its optimum ratio. Then we're also going to evaluate the inclusion of PDMS. PDMS stands for polydimethyl siloxane within the polymer matrix. So we will see how the addition of the PDMS into the polymer matrix actually enhance the surface wettability of the coatings. Okay, that's mainly because of the SiO-Si structure. Okay, and it has this feature where it actually enhances the hydrophobicity nature of the coatings. Then we also want to further evaluate the corrosion protection performance of the polymer matrix, fabricated polymer matrix. We also need to identify whether our multifunctional coatings, the system, whether they are intact, okay, and whether there are any cracks, okay, as we know that cracks do lead to lower corrosion protection performance. So these are the characterizations that were conducted on the fabricated coating system. So we have the Fourier transform infrared spectroscopy, FTIR. Then we have the water contact angle to actually evaluate the hydrophobicity nature of the coatings. Then we have the UV-vis, ultraviolet visible. And then we have the EIS, electrochemical impedance spectroscopy. This is mainly to evaluate the corrosion protection performance. And finally, we have the CHT cross-hatch test that was done according to the standard of ASTM D3359, mainly to evaluate the adhesion of the coatings to the metal substrate. So these are the materials that were used for this study. We used the epoxy resin, Epicot 828. We use the curing agent, Epicure 3388, and then acrylic resin 870BA, and its curing agent NCO, which is also known as polyisocyanate resin. And we also used polydimethyl siloxane PDMS, and isophorone diamine IBDA was mainly to ensure that the cross-linking had occurred between both the resins. So the samples were fabricated as illustrated in table 1. So we have T1 up to T8 samples, and we can see that the acrylic resin to epoxy resin, we had varied the ratio, all right, 8 to 8. So all these were measured in grams, and we kept the PDMS inclusion to be consistent, which was 0.1 grams. And we calculated the IPDA based on the calculation was based on the amount of epoxy used. So 1 to 10 ratio of the IPDA to the epoxy resin used. And then polyisocyanate was used for those samples that contained higher content of acrylic resin. All right. And of course, for the Epicure 3388 was included for those samples that contained higher content of epoxy resin. And then using a alcometer 456 gauge, we actually evaluated the thickness of the coatings for each sample in micrometers. So the methods were very simple. Into a beaker, acrylic and epoxy resin were added, and with a magnetic stir bar, and it was stirred at about 2 to 300 RPMs. And then, of course, IPDA was added, and the coatings were again stirred for an additional 15 minutes. And then finally, PDMS was also added, and the mixture was stirred for a final 10 minutes. So before the curing agent was added to the polymer matrix, the sample was placed into a sonicator. to ensure that the there were no bubbles, or because of the viscosity of the epoxy resin, we wanted to ensure that the mixture was given a homogeneous dispersion. All right. And then finally, when the curing agent was added, a clean glass rod was used, and it was manually stirred for 2 to 3 minutes before it was applied on both sides of the mild steel substrate. Okay, the remaining coating was also used to be applied on one side of the glass substrate, and also it was placed in the remaining coating was placed in a petri dish, so that we could get the film to conduct other testings. So this is the glass substrate samples that was prepared for all the samples ranging from T1 to T8. And now we can talk about the results and discussion. So we can look at the FTIR results from T1 to T8, and we can see that there was a CO band at approximately 1733, which shifted to 1740, and this indicated that there was a cross-linking that had occurred between the coatings or within the polymer matrix. Secondly, is we can see that after 3,500 per centimeter, okay, there was no band, which indicated that all the curing agents, okay, had actually blended well with the matrix, and it did not affect the polymer matrix or the coatings. And finally, the NH bending peak was observed at approximately 1517 per centimeter, and this bend was attributed due to the cross-linking reactions that had occurred between the functional groups that were available in the curing agent as well as the resin. So figure 5 illustrates the FTIR spectra. And of course, there are other peaks as well. So the second one will be the water contact angle. So in this approach, two sets of results were taken. Figure 6 illustrates the contact angle measurements without the inclusion of PDMS, and we wanted to compare with another set of results with the inclusion of PDMS. And we could easily see over here that how significant the inclusion of PDMS was. And we can see that figure 7, T1, T3, T5, and T7 exhibited hydrophilic attributes. However, T2, T4, T6, and T8 exhibited hydrophobic attributes. Moreover, in overall, the values exhibited in figure 7 were way higher compared to figure 6, which was without the inclusion of PDMS, and this clearly indicated that the inclusion of PDMS did enhance the surface wettability of the coatings, because it has a natural hydrophobic behavior and low surface energy with the SiO-Si chain structure. So from here, it was concluded that the highest value exhibited, highest contact angle value was exhibited by the T2 sample, okay, by the T2 sample. Okay, so the next one is the UV-Vis spectroscopy, and it was indicated over here that the T1 and T5 sample, which on an important note, which contained higher content of acrylic resin, which is 80A20E and 90A10E, exhibited the highest optical transparency value from 300 up to 800 nanometers in wavelength. However, the lowest degree of transparency was exhibited by the T2, T4, T6, and T8 samples, and this light scattering, which was reduced, was due to the molecular interactions within the epoxy and diamine networks. So we can see that T2, T4, T6, and T8 contained lower content of acrylic, at the same time having higher content of epoxy, right? So that was important. So 90% of the transmission was exhibited by the T1 and T5 sample. at approximately 89% at 600 nanometers. However, at 500 nanometers, it exhibited approximately 90%. So this was mainly due to the cross-linking that occurred between the polymer matrix, and therefore this enabled the light transmission to be suppressed through the blended coatings. So let's look at the EIS evaluations. The EIS evaluations were conducted over a period of 60 days. So the sample was exposed to seawater conditions, 3.5 weight percentage NaCl, and the values were evaluated, were measured over a period of 60 days. And we can see figure 9, which is the board plots results after the first day of immersion, and we can see that the green one, which is the T5, exhibited the best results, along with T1 and T7, which again contain the highest content of acrylic ratio. So T5 exhibited the best results, and this coating formula was 90A10 epoxy. So 90 to 10 ratio exhibited the best results, and T1, T5, and T7 showed a Z impedance value, or an impedance value of exceeding 10 to the power of 10 ohms centimeter squared. In other words, providing excellent barrier performance, okay, against the corrosion. So how do we actually know what values are actually good? So for coating, anything below 10 to the power of 5, between 10 to the power of 4 to 10 to the power of 5 is considered poor barrier property. 10 to the power of 6 is considered okay, but it's not so good. 10 to the power of 7 to 10 to the power of 8 is considered very good. However, anything above 10 to the power of 9 is considered excellent. Right. So similarly, we also captured the results at the end of the immersion period, which was at the 60 days. And here again, we could see that T1, T5, and T7 still maintained excellent barrier property against corrosion, exhibiting Z impedance values ranging between 10 to the power of 10 to 10 to the power of 11. So which means that even after 60 days, it provided a tortuous pathway for the electrolyte ions to penetrate through the coating metal substrate. So it's taking a much longer time to reach the metal surface. All right. However, for the samples which contained lower acrylic content, all right, exhibited the lowest result, which we could see the blue color one, which was T6. It has the lowest acrylic content of 10 acrylic to 90% epoxy. So which clearly shows that much higher content of epoxy was not favorable for enhanced corrosion protection performance. This was mainly because of the viscosity, all right, and of course due to the cross-linking of the epoxy resin. So this is the breakpoint frequency graphs to support the results, and we can see that there are two reagents in figure 11. We have the red one, which is the resistive, and the green one, which is the capacitive. So this breakpoint frequency actually indicates that a capacitive, a majority capacitive reagent indicates that the coating is intact, and it also provides excellent barrier protection performance against the corrosion. Okay, so we can see that the sample T1 to T8 in the sequence of A to H, and we can see that for E, figure 11E, which illustrated T5 sample, and of course figure F, which illustrated T7 samples, and T1, which is A, T1, T5, and T7 A, E, G illustrated, okay, a complete or almost complete capacitive reagent, which were in line with the results demonstrated in the EIS over a period of 60 days. However, figure 12 illustrates the breakpoint frequencies at the end of the 60th day of immersion, and we can still see over here that figure A and figure E, which is T1 and T5 samples, still maintained a complete capacitive reagent. However, G it started to show that the electrolyte ions have quickly penetrated, okay, through the layers of the coating. However, it still maintained a strong barrier against the corrosion attack. So this table 2 illustrates the recorded Z impedance value, okay, at 0.01 hertz for all the polymer matrix that were fabricated and exposed, and the coatings were exposed up to 60 days of immersion. So our focus would be on T1, T5, and T7. And let's look at T5, for example. The corrosion protection performance or the Z impedance values were seen to be maintained at a order of magnitude of 10 to the power of 10. Similarly, for T1 and T7, it's still maintained in the same order of magnitude. However, for the remaining samples, for example, the T2, T4, T6, and T8, we could see that some of the samples had a order of magnitude reduced by 1, which indicated that poor performance of corrosion protection against the electrolyte, the penetration of the electrolyte ions. So it would reach the metal substrate interface at a faster rate. So then the final test was done, which was the crosshatch test according to the ASTM D3359-17 method B standard. And a tape test was also conducted, okay, to measure the surface adhesion of the coatings to the metal substrate. And we could see that T1, T5, and T7, which was A, E, and G, exhibited 5B ratings, which means there was zero detachment of flakes, which indicated that the coatings were intact. However, T2, T4, and T8, figure 13B, D, and H, exhibited 4B ratings. There was just a slight detachment of flakes, less than 5%, which was still good. However, for T6 and T3, figure 13C and 13F, we could see that there was a significant detachment of flakes, and therefore this exhibited a 3B rating. Okay, so it's between 55 to 15% of detachment of flakes, which all the results exhibited in the CHT were in complete agreement with the water contact angle results, the EIS, as well as the breakpoint frequencies, okay, which indicated why the samples containing the highest acrylic content exhibited the best results. So the conclusion over here is that how do we know which is the optimum ratio of the combination of the polymer matrix containing the mixture of acrylic and epoxy? So there were many papers which stated only that the researchers only published the use of the combination, for example, 70 acrylic, 30% epoxy. However, there was no technical paper published to explain the different combinations and to why certain combinations of acrylic to epoxy was used. And therefore, in our study, we have actually explained the significance of each combination. And out of all the samples from T1 to T8, the T5 exhibited the best results. Okay, and of course, which contained 90% of acrylic and 10% of epoxy. So the low surface energy of PDMS resulted in the alteration of the surface wettability of the coatings towards a more hydrophobic attribute. So in this case, we also saw the results, which was compared without the inclusion of PDMS and with the inclusion of PDMS. And therefore, PDMS is significantly vital to be included or to be added into the polymer matrix to enhance the surface wettability due to its attributes of having a hydrophobic nature and low surface energy. The co-action effect of the binder that was present in the polymer matrix was also an active reinforcing agent due to the matrix filler and the coating metal interface in the presence of electrolyte ions. So we also saw in the FTIR and also in the other results, how important the IPDA was to ensure the occurrence of the cross-linking between the acrylic and epoxy matrix. So overall, the importance of PDMS as a suitable modifier was illustrated, was demonstrated, and also it was revealed, and therefore T5 was the best coating system to prevent the metal substrate from corrosion attack, okay, which can be very useful for exterior applications. Hence, the results that were exhibited in this study were in complete agreement with the novelty and similar studies that were conducted in the past years, in the sense that higher acrylic content compared to epoxy was much more favorable for excellent barrier property against the corrosion. Okay, so these are some of my papers that were published in the past, Scopus and ISI Index. And number 4 was actually the paper that was published in the Journal of Polymer Research. So you can, anyone is able to view this paper in Google Scholar. Okay, these are some of my book and book chapters published in the past related to corrosion applications, as well as the importance of nanomaterials or nanoparticles to enhance the corrosion protection performance. These are some of my achievements at both at all platforms, local and international exhibitions. These are the certificates that were obtained with respect to the achievements, and this is the reference to the study. Okay, so thank you so much for. I would like to take this opportunity to thank the organization committee for giving me this opportunity to be a part of this conference. Thank you, and if you do have any questions, please feel free to ask.